Hello everyone, this is Professor Roman. Let's continue the field theory lectures. We've been talking about various types of algebraic extensions, the simple algebraic extensions and the finite and finitely generated algebraic extensions, which turn out to be the same thing. Let's take a look now at general algebraic extensions. Let's first note that if Fe is an extension and S is a subset of E, and F with S adjoined is algebraic, then every element of F with S adjoined is a rational function in the elements of S over F with coefficients in F. And therefore, there exists a finite subset S0 of S, such that alpha lies in F with S0 adjoined. And therefore, an earlier theorem implies that alpha is actually a polynomial in the elements of S over F. Also, if F with S adjoined is algebraically generated, so that means the elements of S are algebraic, then, as we just mentioned, every element in F with S adjoined belongs to F with some finite subset S0 adjoined. And so F with S0 adjoined is finitely generated by algebraic elements, and therefore this extension is algebraic. And so beta belonging to F S0 is algebraic over F. So algebraically generated extensions are in fact algebraic extensions. We knew that for finitely generated extensions, and now we know it for all algebraic extensions. Or for all generated extensions, whether this generating set's finite or not. So this is the theorem that summarizes. Fe is an extension, S is a subset of E. If F with S adjoined is algebraic, then the elements of Fs are polynomials in S over F. And Fs is algebraic if and only if every element of S, the generators, are algebraic. Or put another way, for field extensions, the concepts of algebraic and algebraically generated are equivalent. All field extensions, Fe, contain algebraic elements, because every element of the base field, F, is algebraic over F. Of course, there may be elements of E that are not in F that are also algebraic over F, and the set of all elements of E that are algebraic over F forms an intermediate field, which this requires proof, between F and E. And this is the theorem. I don't know why this is in blue. I have to fix that. Let Fe be a field extension. The set A of all elements of E that are algebraic over F is a field. And it's called the relative algebraic closure of F in E. Relative algebraic closure of F in E. As to proof, if alpha and beta are in A, so they're elements of E that are algebraic over F, then this field is finitely algebraically generated over F. And so it's algebraic over F. Therefore, all of the elements of this field are algebraic over F. And so this field is contained in A. And therefore, alpha inverse, assuming alpha is not 0, of course, alpha plus or minus beta and alpha beta, all these lie in A. A is a subfield of E. The relative algebraic closures example of the real field in the complex field C is C itself. And this follows from the fact that every complex number is in fact a root of a real polynomial. So it's algebraic over R. If little z is complex, then this product x plus z bar is this polynomial, and it has real coefficients. The relative algebraic closure of the rational field in the complex field, this is called the field of algebraic numbers, and I'll denote it by script A. So in other words, the algebraic numbers are the complex roots of rational polynomials. Now we know from our study in the ring theory course that if p of x is a rational polynomial with content c of p, then its roots are the same as the complex roots of the integral polynomial q of x, where p of x equals content of p times q of x. Integral polynomials are polynomials with integral coefficients, integer coefficients. So the algebraic numbers consist of the complex roots of integral polynomials. If you don't remember our discussion of content in the ring theory course, you could certainly go back and look at those videos, or just Google content of a polynomial and read about it. But basically, what you do with p of x is you first multiply by an integer sufficient to clear all denominators of coefficients, and then pull out the greatest common divisor of the integer coefficients you have left as a result of what you just did, and that's the content. And so q of x is an integer polynomial or integral polynomial whose coefficients are relatively prime. Here are some examples of algebraic numbers. Rational numbers are algebraic. All roots of quadratic integral polynomials, of course, are algebraic. The Gaussian integers, we studied these in the ring theory course. These are the polynomials in I over the integers, so a plus bi, where a and b are integers. The trigonometric numbers, which are numbers that are equal to the sine or cosine of a rational multiple of pi. So cosine pi over 7, that's a root of this polynomial. Don't ask me how I know that. I don't remember where that came from. The numbers pi and e are not algebraic numbers. They're transcendental in the first place, so they're certainly not algebraic numbers. They're not even algebraic elements. In the ring theory course, I proved a consequence of Eisenstein's criterion that we will have use for later. Let R be an integral domain that contains at least one prime p. For every positive integer n, this polynomial, x to the n minus p, is irreducible over R. And so in particular, there's an irreducible polynomial of every positive degree over any integral domain. So there is, as a special case, an irreducible polynomial of every positive degree over the integers. That means that the field A of algebraic numbers is an infinite algebraic extension of Q. Another example, this is somewhat of an aside. So we've just seen the algebraic numbers A are the complex roots of rational or equivalently integral polynomials. The subring of A, it's not a field, it's a subring of A, consisting of all complex roots of monic integral polynomials, is called the ring of algebraic integers. So for example, the rational number 1 over m, as long as m is not positive or negative 1, is an algebraic number but not an algebraic integer. And to see that 1 over m is not an algebraic integer, suppose we had an integral polynomial with root 1 over m. Then p of 1 over m is 0. It looks like this. We multiply through to clear the denominators. We get this. Move the 1 to the other side, factor out an m, and we have a problem because m and this quantity in parentheses are integers, which means that m has to be positive or negative 1. So we won't have anything more to say about algebraic integers. It's not a field, but I wanted to give that definition to you anyway, since they're related to algebraic numbers. The class of algebraic extensions is very well behaved. It's strongly distinguished. As for the tower property, suppose that FKE is a tower of length 2. If the full extension is algebraic, then of course the lower step is, because algebraicness is a property of elements. So if all the elements of E are algebraic over F, certainly all the elements of K are. Also, since any polynomial over F is a polynomial over K, the upper step is algebraic. Okay? So if the full extension is algebraic, both steps are. Conversely, suppose that both steps are algebraic. And take an element of, we want to show E is algebraic over F, so we take an element from E. It has a minimal polynomial over K because the upper step is algebraic, so the coefficients here belong to K. And we take a look at this tower, F with the coefficients of this minimal polynomial adjoined, and then we adjoin alpha. Alpha is algebraic over this field because it's exactly what you need to get the minimal polynomial of alpha. So this upper step is a simple extension by an algebraic element, so it's finite. Each of the coefficients, being in K, is algebraic over F, so this is finitely algebraically generated and therefore is finite. And so both of these steps are finite, and therefore the full extension is finite, and therefore it's algebraic, and so alpha is algebraic over F. So Fe is an algebraic extension. For closure under lifting, if Fe is algebraic, and suppose then that K is any extension of F, we have to show that the lifting, Ke, is algebraic. And for this, we can look at the relative algebraic closure of K in Ek. So this is the set of all elements of Ek that are algebraic over K. Well, each alpha in E is algebraic over F, because this is an algebraic extension, and so these elements are algebraic over K as well. And so E is actually contained in A. Because A is by definition the elements that are algebraic over K. Okay? But K is contained in A, and so the composite Ek is a subfield of A, but A is a subfield of Ek, so A equals Ek, and that is therefore algebraic over K. Ek is algebraic over K. So that's the lifting. I have Ek here and Ke there, but it doesn't matter, right? Because that's commutative. Okay. Now, because the class of algebraic extensions has the tower property and the lifting property, we know it's closed under finite composites. But we have a finiteness condition going on here because we're dealing with the elements individually in the definition of algebraic extension. So in particular, if F is an arbitrary family of fields, each algebraic over this is script F, over F, then so is the join, because any element of the join is also an element of a finite composite of elements from script F. In other words, a finite join from members of F. And it is therefore belongs to an algebraic extension, so is algebraic over the base field. So we have talked about relative algebraic closures. But there's another meaning of the term algebraic closure, and it goes as follows. A field E is said to be algebraically closed if any non-constant polynomial over E splits over E. You may know its famous result that the complex field is algebraically closed. Every complex polynomial splits. It has the full set of roots in the complex field. A field E is an absolute algebraic closure, and I think I kind of invented the term here because it's usually just called an algebraic closure. But just temporarily for emphasis, I wanted to separate this from the idea of a relative algebraic closure. So you probably won't hear this phrase elsewhere. It'll just be called an algebraic closure. So E is an algebraic closure of F if Fe is algebraic and E is algebraically closed. We're going to have many occasions to refer to an algebraic closure of a field. It's not unique, but as we will see later, all algebraic closures of a field are isomorphic. we have to prove they even exist, which we'll do. But I mention this now because I'm going to use an overbar for an arbitrary algebraic closure of F, probably unspecified, just pick any algebraic closure, fix any algebraic closure. The overbar is a fairly standard notation, I think, for the algebraic closure, but it may not be universal. So we'll note the following. A field E is algebraically closed if and only if every non-constant polynomial has a root in E. That will imply that every non-constant polynomial over E actually splits over E. An algebraically closed field E has no non-trivial algebraic extensions, so EK. So if this was an algebraic extension, E is algebraically closed, then since any alpha in K is algebraic over E, it has a minimal polynomial over E, but that polynomial has to split over E because E is algebraically closed, so all its roots, including alpha, belong to E. So anything in K is also in E, so this is a trivial extension, K equals E. Example, the field script A of algebraic numbers is by definition the relative algebraic closure of Q in the complex field C. So this is in fact algebraic, but the algebraic number field is also algebraically closed. And to prove that, we will borrow a result that I mentioned a minute ago that we're going to prove much later in the book, that C is algebraically closed. That's actually called the fundamental theorem of algebra. Okay, so suppose we have a polynomial over the algebraic numbers, non-constant polynomial, and let R be a root in the complex numbers. That's where we use the fact that C is algebraically closed, because this is a complex polynomial, non-constant, so we'll have a root in. Then this tower, Q to A with R adjoined, the root adjoined, is algebraic. And so R is algebraic over Q, and so R belongs to script A. And so P of X has a root in A. P of X was an arbitrary non-constant polynomial, so as we remarked a few minutes ago, P of X will split over A, and so A is algebraically closed. So A is an absolute algebraic closure of Q. It's defined as the relative algebraic closure of Q in C, but this shows that it is in fact an absolute algebraic closure as well as a relative algebraic closure. On the other hand, the relative algebraic closure of Q in the real field, so that's an intermediate field K of all real numbers that are roots of rational polynomials. So QK is algebraic. Everything in K is a root of a rational polynomial. But K is not algebraically closed. For example, this rational polynomial has no roots in R, let alone K. So this is a relative algebraic closure that's not an absolute algebraic closure. So the concepts are different relative and absolute algebraic closures. This first part of this example, though, is not an isolated case. If we have a field and it's contained in some algebraically closed field E, just as we had here, Q is contained in C, and we let A be the relative algebraic closure of the small field in the algebraically closed field, then A is in fact an algebraic closure. It's absolute. First, of course, FA is algebraic. To see that A is algebraically closed, the argument in the previous example works just as well in general. So we have a polynomial over the relative algebraic closure, non-constant. It has a root in E. This is the critical part of the argument. E is algebraically closed, contains A. Therefore, there's a root of this polynomial. And we can look at this same tower, essentially, we looked at before. It's algebraic, so little r is algebraic over F, and therefore, by definition, little r is in A, and so P of x splits over A. And that means A is algebraically closed. What's really important about this is that it gives us a segue into showing that every field has an extension that's algebraically closed. And to show that it's sufficient to show that every field is contained in some extension that is algebraically closed, then that would mean that every field has, in fact, an algebraic closure. Here's the proof. So this is, F is a field, there is an extension, E of F, that is algebraically closed. And I'll say again, that means that F, any field F, has an algebraic closure. It will be the relative algebraic closure of F in E. And as I say, it's not necessarily unique because E is not necessarily unique. This is a proof due to Émile Artin, who we spoke about a fair amount in the ring theory course. We want a field extension Fe for which every non-constant polynomial over E has a root in E, because we're trying to find a field E that's algebraically closed, an extension of F. But suppose instead that we can do something less ambitious. Suppose we can find an extension E of F for which every non-constant polynomial over the base field F, not necessarily over E, but just the base field F, has a root in E. If we could do that, then we can find an extension F1 of F for which every non-constant polynomial over F has a root in F1. Then we can do the same process again, find an extension F2 of F1 for which every non-constant polynomial over F1 has a root in F2, and so on. We can build a tower in which each non-constant polynomial over a given field Fk has a root in the next field in the tower. Then we take the union of all these. This is a chain of fields. The union is a field. It's an extension of F. And any polynomial over this union has only a finite number of coefficients, so they'll belong to one of the members of the tower, Fk, And so it'll have a root in fk plus 1, and in other words, in E. And so E will be algebraically closed. That's a very clever idea that's relatively simple once you understand it, as a lot of ideas are. Not so simple before you understand it. So the proof will be complete if we can just do this once, because then we just repeat it. So we need to find a field F1 with the property that every non-constant polynomial over F has a root in F1. And to do that, to find F1, we manufacture a root for each non-constant polynomial over F. So if P of X is such a polynomial, we let X sub P be a formal symbol and collect all of those into a set. This is a set of independent variables. And let R be the ring of polynomials over these manufactured variables, one for each polynomial. So this is the ring of all polynomials in the variables script X over F. It's only a ring, but we can produce a field and at the same time turn XP into a root of P of X by factoring R by a maximal ideal that contains these elements, these polynomials P of XP, because that'll essentially turn them into 0. And so every polynomial over F will have a root in the bigger field. So to this end, we first have to show that the ideal generated by these polynomials is proper in R, and therefore is contained in a maximal ideal. We proved in the ring theory course that every ideal is contained in a maximal ideal. Proper ideal is contained in a maximal ideal. If I is the whole ring, we need a contradiction. Then there would exist non-zero polynomials in R and non-constant polynomials over F, for which this linear combination was equal to 1. Remember, I is the ideal generated by these polynomials. So if that ideal is all of R, then every element, including 1, can be reached within this ideal, is an element of this ideal. And so it's a polynomial combination of some of these polynomials that generate I, of the generators of I. Well, this is an expression over F. All of these polynomials are polynomials over F. They belong to the ring R. In a finite number of the variables from X. Be clear on this notation, this common notation, Q1 of X. X here is an infinite set, but this is a polynomial. It's not a polynomial in infinite many variables. It's an ordinary polynomial where the variables come from the set script X. Okay? So there are only a finite number of variables from script X in this equation. Now, earlier theorem, quite a bit earlier, implies there's an extension of the base field, extension E of F, in which each of these polynomials has a root. There's only finitely many polynomials here, and let's say the roots are alpha 1 through alpha n respectively. Then thinking of this equation as an equation over the extended field E, we can set each variable to alpha I, and all this will become 0, but this side is 1, and that's a contradiction. So I is proper in R. Hence, there is a maximal ideal J containing I, a proper subset of R, and F1 we can take to be R mod J. This is a field. Each non-constant polynomial, P of x, one of the generators of I, has a root P of capital XP is one of the generators of I, and it has a root XP plus J. This coset, because we factored out by J. So P of XP belongs to J, so P of this is J, which is 0 in the quotient ring, or the field. So we can think of F1 as an extension of F. It's not literally an extension, but if we identify the elements of the base field F, say alpha, with the coset, then F is in fact embedded in F1 isomorphically, so we can think of F as the embedding, and then F1 is a true extension. We've been through this a couple times before, and I went into detail on this in the volume on ring theory. It's kind of common to blur this isomorphism and not really worry about it. That's a fairly common thing to do. When we talked about the characteristic of a field, the prime subfield of a field of characteristic 0 being Q, the rationals. It wasn't literally the rationals, but it was a subfield isomorphic to the rationals, and it is customary to think of the rationals themselves as contained in any field of characteristic 0. So this is a fairly common thing to do. So theorem 1.59 we just did shows that every field F has an extension E that's algebraically closed, and we've already seen that the relative algebraic closure A of F and E is an absolute algebraic closure of F. So every field has an algebraic closure. Moreover, A is the only algebraic closure of F that's contained in E. Because if B was another algebraic closure of F, also contained in E, then these two extensions are algebraic, and so this extension is algebraic. And therefore, so are these steps. But algebraically closed fields, such as A and B, do not have non-trivial algebraic extensions, and so A is equal to AB and B is equal to AB, so A and B are equal. So corollary, every field F has an algebraic closure, and in fact, if FE is an extension and E is algebraically closed, then the relative algebraic closure of F and E is the unique algebraic closure of F within E. And as I mentioned a few moments ago, we're going to show later that all algebraic closures of a field are isomorphic. So We can characterize algebraic closures in a very nice way. In fact, a way that will look familiar to you. We know from our study of linear algebra that a subset B, script B of a vector space V is a basis for V if and only if it's a maximal spanning set for V or a minimal linearly independent set in V. And we have something analogous going on here. Let Fe be a field extension. The following are equivalent. E is an algebraic closure of F. E is a maximal algebraic extension of F. And you should be able to fill in what that means, but here it is. Fe is algebraic, and if Fek and Fk is algebraic, then K equals E. Also equivalent is E is a minimal algebraically closed extension of F. And also Fe is algebraic, and every non-constant polynomial over F splits over E. That's not the definition of algebraic closure. It would be every non-constant polynomial over E splits over E. So this is, we dealt with this before. All right. Statement 1 implies statement 2. If E is an algebraic closure of F, then E is a maximal algebraic extension. Because an algebraically closed field has no non-trivial algebraic extensions. We talked about that, so we essentially did this earlier in a different language. Conversely, if E is a maximal algebraic extension of F, then E does have an algebraic closure, so we have this tower, and E bar is algebraic, but E is a maximal algebraic extension, therefore E and E bar are equal, and so E is algebraically closed. So E is both algebraic over F and algebraically closed, therefore it's an algebraic closure of F. So 1 and 2 are equivalent. To see that 1 implies 3, suppose we have this tower where K is algebraically closed. Okay. We're trying to show now that if E is an algebraic closure of F, then E is a minimal algebraically closed extension. So here is an algebraically closed extension. Contained in E, we need to show E and K are equal. The full extension is algebraic, because E is an algebraic closure of F. The upper step is algebraic. But K, being algebraically closed, has no non-trivial algebraic extensions. Therefore, K and E are equal. So E is minimal with respect to being algebraically closed over F. Conversely, suppose E is a minimal algebraically closed extension of F, then we've seen in the previous corollary that the relative algebraic closure of A, call it A, of F and E is the unique algebraic closure of F contained in E. And so the minimality of E implies that E equals A is in fact an algebraic closure of F. Finally, it's clear that 1 implies 4 because we've weakened the set of polynomials that must split. Any polynomial over E splits over, if any polynomial V splits over E, then any polynomial over F splits over E. For the converse, suppose that this seemingly weaker statement holds, then we have to show that every non-constant polynomial over E splits over E. Well, if E bar is an algebraic closure of E, then f of x, this polynomial of E, does split over E bar. But if we take a root in E bar of this polynomial and form this tower, it is algebraic. Fe is algebraic, lambda is algebraic over E, so the upper step is algebraic. So the full extension is algebraic, right? Each step is algebraic. And so the full extension is algebraic. And so lambda is algebraic over F. This is an argument we've seen before. So the minimal polynomial of alpha over F splits over E, because we're assuming that polynomials over F split over E, and therefore lambda is in E. And so f of x splits over E, and E is algebraically closed.